Sit tight, grab a snack. This is going to be a long video. According to some models of the Big Bang Theory, the universe was initially a singularity, which is a point in space-time where the quantities that are used to measure the gravitational field become infinite in a way that does not depend on the coordinate system. The instant immediately following the initial singularity is part of the Planck Epoch, the earliest period of time in the history of our universe. The very early universe, also known as the Planck Epoch, is the earliest period of time in the history of the universe, before the time passed was equal to the Planck time, TEP. That is from 0 to approximately 1043 seconds. During this time, the universe was extremely hot and dense, and even subatomic particles could not form. The four fundamental forces that shape our universe were combined and formed one unified fundamental force. After the Planck Epoch, the universe entered the Grand Unification Epoch, where gravity separated from the other fundamental forces and began operating on the universe. The remaining fundamental forces stabilized into the electronuclear force, also known as the Grand Unified Force or Grand Unified Theory, QT. According to inflation theory, during the Inflationary Epoch about 1032 of a second after the Big Bang, the universe suddenly expanded, and its volume increased by a factor of at least 1078, an expansion of distance by a factor of at least 1026 in each of the three dimensions. This would be equivalent to expanding an object 1 nanometer, 10^9 mem, about half the width of a molecule of DNA, in length to one approximately 10.6 light years, about 1017 m or 62 trillion miles long. As the universe continued to cool and expand, it entered the electro-weak epoch, where the strong nuclear force became distinct from the electro-weak force. This separation may have fueled the inflation of the universe. In the first moments after the Big Bang, when it was just 100 millionth its current size and its temperature was extreme, 273 million degrees above absolute zero, conditions became just right to give rise to quarks and electrons, building blocks of matter. A few millionths of a second later, quarks aggregated to produce protons and neutrons. Within about 3 minutes after the Big Bang, conditions cooled enough for these protons and neutrons to form hydrogen nuclei. This is called nucleosynthesis. The cosmic microwave background, CMB, is leftover radiation from this time when atoms formed. The CMB dates back to about 400,000 years after Big Bang. The radiation from CMB photons was scattered off electrons. About 380,000 years after Big Bang, when hydrogen formed, CMB photons travel in straight lines because they are barely affected by hitting hydrogen. The early universe lasted around 370,000 years. Initially, various kinds of subatomic particles are formed in stages. These particles include almost equal amounts of matter and antimatter, so most of it quickly annihilates, leaving a small excess of matter in universe. At about 1 second, neutrinos decouple. These neutrinos form cosmic neutrino background, CNB. If primordial black holes exist, they are also formed at about 1 second of cosmic time. The Cosmic Dark Ages is a period in the history of the universe that lasted for about 1 billion years after the Big Bang. During this time, the universe was enveloped by a fog of neutral hydrogen that trapped the light of the first stars and galaxies. The Cosmic Dark Ages only fully came to an end when the neutral hydrogen had been re-ionized and once again split apart. The Cosmic Dark Ages were a time of great transformation. This period is special in the sense that it marks the transition between the universe being very simple and being very complex, says Avi Loeb, an astronomer at the Harvard-Smithsonian Center for Astrophysics. The tiny perturbations visible in the cosmic microwave background transformed into the large-scale structures that we see throughout the universe today. The end of the Cosmic Dark Ages is thought to have occurred sometime between 300 million years and 1 billion years after the Big Bang. Current models of the universe suggest that the first galaxies began forming about 100 million years after the Big Bang, marking the beginning of the end of the Dark Ages. The Re-ionization Epoch is a period in the history of the universe during which the predominantly neutral intergalactic medium was ionized by the first stars and galaxies. It is believed to have occurred between 400 million years and 1 billion years after the Big Bang. A group of astronomers led by Sarah Bosman from the Max Planck Institute for Astronomy have robustly timed the end of the epoch of re-ionization of the neutral hydrogen gas to about 1.1 billion years after the Big Bang. This process lasted 200 million years longer than previously thought. During this period, the universe underwent a second major phase transition after recombination, where electrically neutral atoms in the universe were re-ionized after the lapse of the Dark Ages. The universe was opaque before recombination due to the scattering of photons off free electrons, but it became increasingly transparent as more electrons and protons combined to form neutral hydrogen atoms. The second phase change occurred once gas clouds started to condense in the early universe that were energetic enough to re-ionize neutral hydrogen. One means of studying re-ionization uses the spectra of distant quasars. Quasars release an extraordinary amount of energy. In fact, they are among the brightest objects in the universe. As a result, some quasars are detectable from as far back as the epoch of re-ionization. After the cosmic microwave background formed 400,000 years after the Big Bang, all the universe's hydrogen gas was in atomic form, an electron orbiting each proton. But this did not last. Massive stars produce enough energy to tear apart or ionize hydrogen, separating protons and electrons. Formation and Hadeon Eon, 4.0 billion years ago. Earth formed around 4.54 billion years ago by accretion from the solar nebula, a disk of gas and dust that surrounded the young sun. The early Earth was bombarded by asteroids and comets, which caused intense volcanism and outgassing of water vapor, carbon dioxide, nitrogen, and other gases. The Moon formed as a result of a giant impact between Earth and a Mars-sized body named Theia, about 4.5 billion years ago. The Earth's surface was mostly molten with a thin crust that was constantly recycled by plate tectonics. The first oceans formed as the Earth cooled and water condensed from the atmosphere about 4.4 billion years ago. The first signs of life may have appeared as early as 4.1 billion years ago, in the form of microscopic organisms that used carbon dioxide and water to produce organic molecules. Archean Eon, 2.5 billion years ago. The Archean Eon was characterized by the emergence and diversification of prokaryotic life forms, such as bacteria and archaea. The Earth's atmosphere was still mostly devoid of oxygen, but some microbes developed the ability to perform photosynthesis, using light energy to split water molecules and release oxygen as a byproduct. The first stromatolites, layered structures formed by microbial mats, appeared about 3.5 billion years ago in shallow waters. The first continents began to form as the crust stabilized and thickened, creating land masses such as Valbara, and Kenorland. The Earth experienced several cycles of global glaciation, known as snowball Earth events, during which ice sheets covered most or all of the planet's surface. Protozoic Eon, 2.5 billion, 541 million years ago. The Protozoic Eon witnessed the rise of eukaryotic life forms, which have complex cells with nuclei and organelles. The first eukaryotes may have originated from endosymbiosis, a process in which one cell engulfs another and they become mutually beneficial. The first multicellular organisms appeared about 1.8 billion years ago in the form of algae and fungi. The first animals emerged about 800 million years ago in the form of simple sponges and cnidarians. The oxygen level in the atmosphere increased significantly during the Great Oxygenation Event, about 2.4 billion years ago, and again during the Neoproterozoic Oxygenation Event, about 580 million years ago. The Earth experienced another series of snowball Earth events between 750 and 580 million years ago, which may have triggered the evolution of complex life forms. Paleozoic Era, 252 million years ago. The Paleozoic Era began with a Cambrian explosion, a rapid diversification of animal life that produced most of the major phyla that exist today. The first vertebrates appeared about 525 million years ago in the form of jawless fish. The first plants colonized the land about 470 million years ago, followed by the first arthropods and fungi. The first land vertebrates appeared about 370 million years ago in the form of amphibians that could breathe air and water. The first reptiles evolved about 320 million years ago, which had scaly skin and eggs that could survive on dry land. The first insects appeared about 300 million years ago, which became the most diverse and abundant group of animals on Earth. The first seed plants appeared about 280 million years ago, which could reproduce without water and dominate terrestrial ecosystems. The Paleozoic Era ended with the Permian-Triassic extinction event, the largest mass extinction in Earth's history, which wiped out about 95% of all species on Earth, possibly due to volcanic eruptions or asteroid impacts. Mesozoic Era, 66 million years ago. The Mesozoic Era was the age of the dinosaurs, which evolved from reptiles and became the dominant land animals for over 150 million years. The first dinosaurs appeared about 230 million years ago in the form of small bipedal carnivores. The first mammals appeared about 210 million years ago in the form of small nocturnal insectivores that lived in the shadow of the dinosaurs. The first birds evolved about 160 million years ago from feathered theropod dinosaurs that could fly. The Mesozoic Era ended with the Cretaceous-Paleogene extinction event, the second largest mass extinction in Earth's history, which killed about 75% of all species on Earth, including most of the dinosaurs. The Cenezoic Era is the current era of Earth's history. The first primates appeared about 55 million years ago in the form of small arboreal mammals that had grasping hands and large brains. The first whales evolved about 50 million years ago from land mammals that returned to the water and adapted to aquatic life. The first grasses appeared about 40 million years ago, which created new habitats for grazing animals and shaped the evolution of teeth and digestion. The first hominins appeared about 7 million years ago in the form of bipedal apes that diverged from chimpanzees and bonobos. The first civilizations appeared about 6,000 years ago in the form of organized societies that had agriculture, writing, and laws. The current year is 2023 AD. Halley's Comet flyby, 42 years. Deneb becoming a new pole star due to axial rotation, 7,780 years. Ross 248 being the new closest star at 3 light years, 34,000 years. New volcanic Hawaiian island called Loihi, 50,000 years. Betelgeuse supernovae being brighter than a full moon and lasting as long as a month, up to 100,000 years. Gliese 710 getting alarmingly close to the sun at 0.2 light years, 1.29 million years. Phobos collision with Mars, resulting in a new ring system, 30 to 50 million years. Saturn's rings, decaying and colliding with Saturn, 100 to 300 million years. Andromeda Milky Way collision forming Milkdro-Meta, about 4.5 billion years from now.
The Sun is currently a main sequence star that fuses hydrogen into helium in its core. As it ages, it will gradually increase its luminosity and temperature, making the Earth hotter and drier. In about 5 billion years, the Sun will exhaust its hydrogen fuel. This will cause it to expand into a red giant star that will engulf Mercury and Venus and possibly reach the orbit of Earth. The Earth will become uninhabitable for life as we know it, as the surface temperature will rise above 1,000 degrees and the oceans will boil away. The atmosphere will also be stripped by the intense solar wind. The observable universe shrinks to the local group in 2 trillion years, as dark energy pushes everything else away. In 1 quadrillion years, 1,000 trillion, all planets are ejected from their orbits and exposed to the cold dark of space. In 1 quintillion years, 1,000,000 trillion, the objects that were once stars are also ejected from their galaxies. The last white dwarfs become black dwarfs in 10 to the 45 years. cold black objects that are invisible due to almost no light emitted in the universe. In 10 to the 45 years, even subatomic particles decay, and the black hole era begins. Though proton decay is a theory, we will come back to it later. Back to the black hole era, galaxies are just a big black hole with more black holes orbiting it. In this time, black holes are the new fundamental building block. We don't yet understand dark matter or dark energy, so we don't know the future, or even our own origins. Depending on what happens to dark matter, these are the possible endings of the universe, the big crunch. Gravity overcomes the expansion of the universe and pulls everything back together, reversing the Big Bang and destroying the universe in a singularity. The Big Rip. The expansion of the universe accelerates so fast that it overcomes gravity and other forces, tearing apart galaxies, stars, planets, atoms, and even space itself. The Big Freeze. The expansion of the universe continues at a steady rate, leading to a cold and dark cosmos where all matter and energy are diluted and dispersed. These are the most widely accepted theories. But even black holes are not forever. They too will fizzle away from Hawking radiation, named after legend Stephen Hawking. This is his explanation of his Hawking radiation.
Quantum mechanics implies that the whole of space is filled with pairs of virtual particles and antiparticles that are constantly materializing in pairs, and then coming together again and annihilating each other. One member of a pair of virtual particles may fall into the hole, leaving the other member without a partner with which to annihilate. The forsaken particle or antiparticle may fall into the black hole after its partner, but it may also escape to infinity, where it appears to be radiation emitted by the black hole. The message of this lecture is that black holes ain't as black as they are painted. They are not the eternal prisons they were once thought.
Eventually, after a Google years, or one with 100 zeros, even the black holes will have evaporated and will die. In a fiery and bright explosion, the final light of the universe. But wait, what if protons don't decay? Then there is another scenario that could happen. In this scenario, all mass in the universe will clump together due to gravity and turn into iron-56 stars. Iron-56 is the most stable element in the periodic table, and it has the lowest energy per nucleon. This means that it cannot undergo any further nuclear fusion or fission reactions. These iron balls will be the last things in the universe, roaming in space forever. Unless, like Stephen Hawking said, space is full of virtual particles. Pairs of particles and antiparticles that pop into existence and annihilate each other in a fraction of a second. These particles could cause a change in energy, defying entropy and creating a new Big Bang. But this will take an extremely long time, about 10 to the 10 to the 56 years. This is such a huge number that it is hard to comprehend. Who knows what could happen in the new universe? If you watched this video to the end, congrats. You are smarter than you were 20 minutes ago. Thanks for watching.